Today, we're going to talk about something you can't see, but it's literally everywhere. It's the invisible architecture of our entire universe, the cosmic glue that holds all matter together. Yep, we're talking about the chemical bond.
I mean, really think about that for a second. What's the force that keeps the atoms in your body from just flying apart? What holds the water in the ocean together or forges the steel in a skyscraper? It sounds impossibly complicated, right? But the answer is actually pretty amazing and elegant.
Because really, it all just comes down to this: a fundamental force of attraction, a simple pull between the tiniest building blocks of matter. This force, well, this is the hero of our story today.
And it has an official name, of course, the chemical bond. The textbook definition is the force of attraction that keeps two or more atoms together. Simple, right? It's what links atoms to form everything from the oxygen we breathe to the crazy complex DNA in our cells. So the real question is, how does this attraction actually work? Well, it turns out that atoms have a few different moves in their playbook. They're not one-trick ponies. They have three main strategies for connecting with each other, and each one has its own unique personality. So let's meet the cast of characters, shall we? First up, we've got the most dramatic relationship of the bunch. I like to call this one the giver and the taker. This is our introduction to the world of ionic bonds, and it's a story all about transfer and attraction. Okay, check out this classic example. You've got a sodium atom over here, and it has one extra electron it would just love to get rid of. Then you have chlorine, and it's just one electron short of being perfectly happy and stable. So what happens? Sodium gives its electron away, and chlorine eagerly snatches it up. And that one little action, it changes everything. You see, by losing that electron, sodium becomes positively charged. And by gaining one, chlorine becomes negatively charged. And what do we know about opposites? They attract. It's like a magnetic force pulling them together, and that attraction is the ionic bond. This whole strategy is the classic partnership between metals, the givers, and nonmetals, the takers. And it's exactly what creates the salt sitting in your kitchen shaker. But, not all atoms are into that whole give-and-take drama. Some of them prefer a more cooperative approach. And that brings us to our second strategy: the art of sharing, better known as the covalent bond. The perfect example of this is a molecule we all know and love, water, H2O. You've got one big oxygen atom that needs 2 electrons and 2 little hydrogen atoms that each need 1. Now, instead of one atom stealing from the others, they all decide to share. They form this tight-knit little group where the electrons just zip around all 3 atoms, holding them all together in a super stable, super strong molecule. So the covalent strategy is really all about cooperation. It usually happens between nonmetal elements who figure out it's just better for everyone to share their electrons to get stable. And this sharing is what creates all these strong individual molecules that make up so much of our world, from the very air we breathe to the plastics we use every day. All right, that brings us to our third and final strategy. And this one is in a league of its own. It's not about giving, it's not about sharing in pairs. It's more like a giant community pool party for electrons. Get ready for the secret of metallic bonds. So get this, in a piece of metal, all the atoms agree to give up their outer electrons, but not to any one specific atom. No, instead, all these electrons jump into a big pool together, forming this free-flowing sea or cloud that just moves among all the atoms. The atoms themselves become these positively charged islands, just kind of floating in this sea of shared electrons. This collective, community-based strategy is totally unique to metals. It's the attraction between those positive metal islands and that negative electron sea that holds the whole structure together so tightly. And here's the cool part. It's that free movement of electrons that gives metals their classic properties, like being able to conduct electricity and heat so well. So let's do a quick recap of the 3 big strategies. You've got your ionic bonds, where electrons are transferred, given and taken, between metals and nonmetals, like in table salt. Then you have covalent bonds, where electrons are shared between nonmetals, like in water. And finally, metallic bonds, where electrons are pooled together in a giant sea by metals, like in a copper pipe. 3 totally different playbooks creating 3 totally different kinds of materials. And that's really the big takeaway here. Whether it's giving, sharing, or pulling, these 3 simple interactions are the unseen architects responsible for building, well, everything around us, from the ground beneath our feet to the stars in the sky. It's an incredible system, right? But it all leads to one final fascinating question. We know these bonds build our world, but they aren't always permanent. So, what happens when they break apart and then rearrange? Well, my friends, that is the story of chemistry itself. Something to think about, isn't it?